talk about one last phenomenon called, so first of all, let me do yet another demo, just because I like doing these demos. We've talked about conservation of angular momentum. So what's going to happen here, notice external torques, external forces. Where's the angular momentum of this system? Up. You saw me how I spun it up. That's right, it's rotating this way. Angular momentum is that way. What happens when I flip this system over? Nothing happened. Did nothing happen? Why? Is angular momentum conserved in this system? External torques? No, no external torques. There are actually slight frictional torques. No external torques. Okay, so angular momentum is this direction. It's a vector. When I flip this over, the angular momentum of the wheel changes direction, but angular momentum is a vector and it's conserved, so angular momentum of the system as a whole must continue to be upwards. How does the system respond? The other part of the system starts to turn so that my angular momentum will now be twice the magnitude of the angular momentum of the wheel and upwards. So initially I have L of the wheel and my L is 0, and afterwards I will have L of the wheel and my L will be 2L of the wheel up, so that the vector nature of them balances. Okay? So I turn this over and I start to rotate, because now I have the angular momentum of the system. Now I have twice as much angular momentum as the object, and I can turn it back around and stop myself. Okay? And of course, if I start with this system like this, which is a little bit more complex, I can actually go both ways. And that, as it turns out, is how you reorient satellites in space, is by having spinning wheels like this, and you reorient the axes of the wheels so that angular momentum as a whole is conserved, but the body of the spacecraft can change direction. Okay. I encourage you to come up and try this. Let me, since I'm not going to finish with the mathematical